Hi there, welcome back. So we talked about the evidence for dark matter that comes from galaxies, the evidence that comes from clusters of galaxies, but what is dark matter, right? So now we'll try to talk a little bit about what may dark matter be. Just to refresh, we have evidence for dark matter coming from galaxies that shows that there is about 10 times more dark matter than luminous matter in galaxies. We measure masses and clusters of galaxies, and we find that there is about 50 times more dark matter than luminous matter in clusters of galaxies. And there is also evidence from the cosmic microwave background, which I won't discuss here because I think it's beyond what we need to cover. So if you haven't seen that, you might want to go back and look what's the evidence for dark matter videos. But there seems to be some kind of matter there that we don't know what it is. And we call it matter because it attracts things gravitationally. So we are left with pretty much two options. Option number one, dark matter really exists, and we are observing the effects of its gravitational attraction. Or we don't know gravity. Something is wrong with our understanding of gravity. And we don't know how to measure masses because we don't know gravity. Okay, so let's examine the two possibilities. We don't know what dark matter is, or dark matter is really, or we don't know gravity or dark matter is really there. So let me start with number two, that something is wrong with our understanding of gravity. There are theories that try to explain how we could possibly correct our understanding of gravity to account for the observations that we see, and that we call dark matter. These theories are called modified Newtonian gravity theories, or MON theories. And it proposes that Newton's second law that says that the force equals the mass times the acceleration is not valid if the acceleration is very small. All right. So if the acceleration is average, the acceleration that we experience every day, it's perfectly fine. But if the acceleration is very small, this Newton's second law will need to be corrected by a certain factor. And that only becomes important when the acceleration is really small, as you see here, about 10 to the minus 10 meters per second square. Those fit perfectly the predictions for rotation curves of low surface brightness galaxies. However, those were developed to fit the rotation curve of those galaxies. The problem is when we try to apply these ideas to other regimes, for example, in the center of massive clusters of galaxies, they don't work. You can't make a correction for small accelerations and have it work in a regime of large accelerations, such as the center of a galaxy cluster. So it could be, but so far we haven't been successful in attempting to correct the theory of gravity. Right? Most astronomers don't believe in MOND. Most astronomers really believe that there is some dark matter out there that we haven't detected yet. But you should be aware that it could be that we just don't know gravity. Now, there are then two options for dark matter, if that dark matter exists. One is, well, it could just be ordinary matter made of atoms like the atoms that make you and I, that we can't see because they are so dim. All right? So, for example, machos. Machos are massive, compact halo objects. Those would be dead stars or stars that never really formed. Very compact objects, but very dark, and we can't see them. But there could be many of them out there that would then account for a large amount of mass. It could also be that there is some intergalactic medium of gas, either warm or colder intergalactic, either warm intergalactic gas or an intercluster medium, right, where there is material that we, for some reason, are not observing, right? So maybe there is something out there, but it's just so cold we can't see. Or it could be neither. It could be something completely new. It could be something we never observed. So they could be wimps, for weakly interacting massive particles. So it's the battle between the wimps and the machos, all right? Now let's go over and try to understand what are the constraints that we have today on machos. So the problem with the idea of machos is that, first of all, we looked for them. We looked for them for a very long time. And because you know everything about gravitational lensing now, you know that if a macho were to pass in front of a luminous object, that object would blink, would become brighter, just for a moment. So even though the object itself may be really dark, when it passes in front of a star, the star behind it will blink, and you should be able to see that. We looked and looked and looked, found some machos, but not enough to be able to account for dark matter. The second problem with machos is that we don't really know where all these heavy elements would be coming from. Because machos wouldn't be made of hydrogen or helium, they would be made of heavier elements. And where would those be coming from? I mean, stars haven't had enough time to create those heavy elements in such a young universe. Okay? So we don't know how we would create so much mass in heavier elements. So maybe not machos, all right? Maybe the machos are losing the battle. They're just not there. Maybe warm intergalactic medium or intercluster medium. Those would be made of mostly hydrogen and some helium. Well, the problem is we know how to observe hydrogen and helium, regardless of how cold or hot they are. Because if they are hot, they are emitting light, and we know how to look for that. If they are cold, it's true they are not emitting anything, but when there's something in the background, the light of that object would be absorbed, and we would see it. So it's just not there. We know how to look for it, and we don't find it. It's not there. So then we are left with the wimps, right? The weakly interactive massive particles. Those will be particles that interact with each other just gravitationally. They don't have a charge, therefore they don't attract each other or repel each other via the electrostatic force. They only attract each other because of gravity. Other than that, they go right through matter. They don't interact a lot. So they are massive, of course. We are looking for a lot of mass, so they better be massive, right? They have a lot of mass. They are weakly interacting. Well, of course they are weakly interacting. If they weren't, we would have seen them already. We would have detected them, right? So that's all the name means. It's something that it doesn't interact much, and it's massive. And we're looking for those particles in big particle accelerators. All right, so actually the dark matter has brought together particle physicists and astronomers to try to solve the mystery. So as of now, our best bet is that dark matter is made of some sort of particle that hasn't been detected in it yet, but it should be detected in the near future. All right, so you just have to keep reading the news, and I hope that helps. See you next time.